All right, today we're going to talk about lines and planes, section 2.5. You'll be responsible for all the goals at the top of the textbook section, with the exception of one small topic that it's just, I don't know, just to save you a little bit of thought. The symmetric equations of a line, in general, I'm just going to ignore that. It's an interesting idea for representing lines, but it's not one that we'll find useful through the remainder of the semester. So the goals here are to understand how to represent and determine equations of lines in 3 dimensions, find the distance from a point to a line in 3 dimensions, to be able to determine and write the equation of a plane in 3 dimensions, to be able to find the distance from a point to a plane in 3 dimensions, and then a somewhat lesser example, but more just to illustrate the idea that I want you to be able to answer questions about the geometry of planes and lines and how they're related to each other. So finding the angle between 2 planes, great, but more broadly, just kind of the geometry of lines and planes. For example, if I ask you to find a line that's parallel to a plane, or if I ask you if 2 lines are going to intersect, or whether they're parallel, or maybe find a line that's perpendicular to another plane. So finding the angle between 2 planes, in my mind, is really just sort of a sub example of the broader idea of being able to take a geometric description of a situation and be able to formulate the line or the plane as needed. This is going to use tools from earlier sections, in particular the dot product and the cross product. What's the big idea here? So we spend a lot of time learning about lines in Calc 1, you know, y equals mx plus b and all of that, and we talk about tangent lines. And the main reason we talk about tangent lines is because in some sense tangent lines can be approximations near a point for a more complicated function. And we use these kinds of approximations in computational tasks, in applications quite a lot. The new thing here, now that we're moving from 2 dimensions, the xy plane, up to 3 dimensions, the xyz coordinate axis, we've got some new objects. In particular, we still have lines, but lines are a little bit different in how we describe them. And now we have a new kind of object, a plane, which, you know, for lack of a better example, is really just a flat piece of paper. It's like a flat piece of paper extending indefinitely in all directions. Well, if you think about, like, a line is still a line. In 3 dimensions, 2 points define a line, or a point and a direction define a line. Planes are new. Planes have an orientation and a position. And we're going to describe the orientation of a plane by specifying a vector that is normal to the plane, that's perpendicular to the plane. And then we're going to specify the plane's position by specifying a point that lies on the plane. So if we specify a point on the plane and a normal direction, we can get the entire variety of possible planes in 3-dimensional space. Planes are useful because we can find tangent planes to surfaces in the same way that we found tangent lines to curves in Calc 1. We can find tangent planes to surfaces and perform a lot of useful applications with them as approximations to more complicated surfaces. Okay, so that's the big idea. We're introducing planes and lines in 3 dimensions, and we're just going to get used to how to represent them, how to compute them, how to answer geometric questions about them. So just do a little bit of a flyover before we get to some of the examples. So a line requires a point and a direction. In fact, let me go over to the textbook here. So equations for lines in space, we require a point and a direction. So in Calc 1, we required a point and a slope, or 2 points. in Calc 3, we require a point on the line and a direction, and that direction is going to be indicated by a vector ABC. Once you have that, however, building the line is relatively straightforward. You can write it in vector form like this. So the points on the line x, y, z are simply the points, the coordinates of the point that we know is on the line, plus t times the direction vector ABC. So if we have a line here that passes through the point C and the direction vector ABC, then all of the other points on the line can be reached just by varying the parameter t. This is the vector equation of the line. If you break it up into coordinates, in other words, x equals x naught plus ta, y equals y naught plus tb, and z equals z naught plus tc, those three equations together are known as the parametric equations of the line, and they look like this. For our purposes, the differences between these two representations are quite small. I'll switch back and forth between the vector representation and the parametric representation all the time, and I'll expect you to do the same. Just to kind of give you an intuitive, a better intuitive notion of what's happening with this kind of representation, let me open this up a little bit here. And let's go grab a vector, maybe even a couple of vectors. So let's say that we have a vector that represents the direction of the line. Let's call that vector u. And then let's say we have a point that we want the line to go through. So let's say a point right here. And let's say I want the line through that point in the direction u. Well, what I can do is create a vector. Let's say that the origin is down here. There's the origin. I can create a vector out to that point. So now this is the point P on the line. And this is the vector that gets us from the origin to that point. The way this is going to work is we're just going to move up and down according to t. So if I want to move in the direction of u, I can just keep tacking on copies of this vector u. And I'm going to trace out this line. So the line that goes through the point P is just P plus T times U, the direction vector. So this is the point on the line, and this is the direction. This is not the same as the slope of the line back in Calc 1, but there is a relationship, and I would encourage you to kind of go back and see if you can kind of reconcile the two different representations in 2 dimensions, because in fact this idea also works in 2 dimensions. I just did it for you in 2 dimensions, even though it generalizes to 3 dimensions. All right, the distance from a point to a line, if you have a line with a direction u and a point on the line p, something like that, and you've got some other point, say M, off the line, the distance from the point off the line to the point to the line is the closest distance, right? There are lots of possible distances, right? But this, the one that sort of makes a right angle with the line, this is the closest, and this is the distance that we seek. How do we figure out this distance? It turns out to actually be closely related to the cross product. we can find a point on the line P, and we have this point M, and we can find the displacement vector from P to M, and then compute the projection of PM onto this direction right here. And we actually have a built-in way of doing that. If this angle is theta, and this is the direction, U, we happen to know that this piece right here, this distance, is the magnitude of, well, let me write out the cross product identity. Remember that the magnitude of the cross product of PM with U is equal to the magnitude of PM times the magnitude of U times the sine of theta, the angle between the two of them. And if you look closely at this, this times this is the distance that we seek. That's the distance from the line. So if we solve for those, D equals the magnitude of PM sine theta equals the magnitude of PM cross U divided by the magnitude of U. So we can compute this distance using what we know about the cross product. Some other concepts: in 2 dimensions, lines were either parallel or they intersected. In 3 dimensions, we have sort of more possibilities. In 3 dimensions, of course, 2 lines could be parallel, but they could also be what we call skew, where this line doesn't intersect. There's no intersection here. So it passes above or it passes below the other line. So they're not parallel, but they also don't intersect. And we call that skew. Not parallel, not intersecting. That's a new situation here in 3D. There's not enough room in 2 dimensions for this to happen, but in 3D it happens all the time. In fact, it happens more often than not. Okay, let's move on to planes. So planes are, of course, just flat sheets in 3-dimensional space. And we can use the dot product to define these things. So let's take a flat sheet in 3-dimensional space. Let's say we specify a direction, call it N, and this is perpendicular to the sheet. And then let's say we also want to fix the position of the plane by specifying a point on the plane P. Then the equation or the definition of a plane is really just the collection of points Q such that the vector PQ is perpendicular to the vector N. So the plane is the set of points such that, and let me label those points, the set of points Q such that the displacement vector P to Q is perpendicular to the normal vector. Well, if you'll remember about the dot product provides us a test for perpendicularness, and so we can actually express this relationship mathematically as PQ dot N equals 0. It's the set of points that satisfy that equation. Now, if we go further, go a little bit further, and we let Q be a generic point x, y, z, and we let P be a specific point x naught, y naught, z naught. So P is fixed and Q is allowed to roam. Then the displacement vector PQ looks like this. It's x minus x naught, y minus y naught, z minus z naught, right? We've done this a few times now. And furthermore, if we assume that the coordinates of n are given by a, b, and c, and we compute this dot product, pq dot n, what we get is x minus, in fact, let's say a times x minus x naught plus b, y minus y naught plus c, z minus z naught, and that's supposed to equal 0. And this is the equation of a plane. So if you drop x, y, and z into this equation and it's equals 0, it's a test of membership, x, y, and z is on the plane. If it doesn't satisfy the equation, x, y, and z not on the plane. An alternative way to write this is to pull out the independent variables x, y, and z, ax plus by plus cz, and move the others to the right-hand side, ax naught plus by naught plus cz naught, and write the equation like this. And if you have a keen eye, you might note here that this is actually n dotted with the vector associated with the point P, which we'll call OP, the vector from the origin to P. Another thing to note here is whenever you're presented with an equation that has linear powers of x, y, and z like this, it's easy to identify the normal vector. It's just the coefficients of x, y, and z. In this case, n is a, b, c. I know I'm kind of working in circles there, but if somebody hands you a plane, you can immediately figure out what the normal vector is, or the perpendicular vector, just by plucking off the coefficients of x, y, and z. The coefficient of x is the first coordinate, coefficient of y is the second coordinate, coefficient of z is the third coordinate. A common question that we might have is we're given a plane and we're given a point off of the plane, let's call it M, and we want to find the distance down to the plane. Same as before, we look for that closest distance, and that corresponds to the length of the line segment from M down to the plane that happens to be perpendicular. There are lots of line segments that go down to the plane, only one of them will be perpendicular, and we'd like to find its length. So what is the length of that perpendicular line segment from a point off the plane to a point on the plane? Well, what do we know about the plane? We know that its normal vector is n, and that is perpendicular to the plane. And we also have a point on the plane, P, which we will denote x naught, y naught, z naught. Now, to compute this distance d, all you have to do, if you know n and p, is to find one other point on the plane. Call it q. All right, so honestly, it could even be p. Doesn't really matter. In fact, let's just keep it as p. We won't introduce. You know, we'll call it q. So find another point. Find a point on the plane and construct the vector q to m, just like that. And this should start to look familiar. We're trying to find the projection of q in the n direction, because notice that this line segment whose length is d is parallel to n. So if we can project qm onto n, find the scalar projection, we will find the distance that we seek. So d is actually the scalar projection, which we denote comp n, the scalar projection of qm onto n. So q can be any point on the plane. So you look at the equation for the plane, you find a q that satisfies that equation. You're given m, you compute this vector, and then it's d is just the scalar projection of qm onto n. And just to remind everybody, the scalar projection of qm onto n is the absolute value of qm dotted with n divided by the magnitude of n. So if you want to find the distance from a point off the plane or even a point on the plane to the plane itself, this is the formula to use, and it goes back to the dot product. Let's talk about how planes might interact with each other. Planes are sort of like lines were back in Calc 1. They can either be parallel, like this. It doesn't look very parallel, pardon my drawing. Or they could intersect, something like this. And when they do intersect, they intersect in a line, like that. So parallel or intersecting. There's no such thing as a skew plane in 3D. In 4D, there are skew planes. So you can have a plane in 4 dimensions, 2 planes in 4 dimensions that are neither parallel nor intersect. But we won't get into that. All right. How do you imagine that we might figure out that they're parallel? You can imagine that they'll be parallel if the normal vectors for the 2 planes are parallel. So if n1 and n2 point in the same direction, and I use this double vertical bar notation to indicate that, then they're parallel. And if they're not parallel, if n1 is not parallel to n2, then they must intersect, and they'll intersect in a line. Let's do a quick, let's explore a quick example of 2 intersecting planes, example 2.52. Let's hop over to the textbook and scroll down to example 2.52. Should just search, eh? All right. So we have 2 planes, x plus y plus z equals 0 and 2x minus y plus z equals 0. If you look at these two, you can pick off the normal vectors. The normal vector in the first plane is 1, 1, 1. And the normal vector in the second plane is 2, negative 1, 1. They're not parallel. If they were parallel, then one would have to be a scalar multiple of the other, and that's clearly not the case. There's no way to rescale 1, 1, 1 so that you get 2, negative 1, 1. So they're not parallel, therefore they must intersect. How are we going to figure out what that line of intersection is? In other words, find the parametric equations for the line. Let's walk through the solution here. So it's a bit of work. You take the 2 equations for the line, and notice that if you add them together, you get a cancellation of the y coordinate, which gives me 3x plus 2z equals 0. And I can solve for x in terms of z. Cool. All right. And if you notice, if you take that discovery and you plug it into the first equation, what you're going to be able to do is solve for y in terms of z as well. So now we have x in terms of z and y in terms of z. And this gives us a way of expressing all 3 variables in terms of a single parameter, t. So what happens is we decide to call this quantity t. So let t equal negative 1/3 z. Then y is going to equal t. And z is going to equal negative 3t. How did I figure that out? I just solved for z in terms of t. And finally, x is going to equal 2t. How did I figure that out? Same deal. Just substitute t equals negative 1/3 z into this equation. And what you end up with by representing all three coordinates in terms of a single variable is the parametric equations for the line. X is equal to t, y is equal to t, z is equal to negative 3t. And this is the parametric representation of the intersection of the two planes. And then just a reminder, don't worry too much about the skew lines project at the end, and don't worry too much about the symmetric equations. All right, let's work through some of the examples at the end of the section. We'll start with problem 2.5.246. Let the browser catch up here a little bit. All right, so problem 246. You're asked to find the vector equation of the line, parametric equation of the line, symmetric equations of the line, and parametric equations of the line segment determined by P and Q. Let's grab a copy of that just so we have it all in front of us while we're working. All right, make this a little smaller. All right, we have 2 points on a line. So I'm going to sketch here. There's P, there's Q, and the line that goes between the two of them, like this. Well, we need a direction. We need a direction vector u. We can figure that out just by computing PQ, because the vector that goes from P to Q is in the same direction as the line. And don't worry about PQ. You could also do QP. You'll end up with a correct answer either way. So it doesn't matter the order in which you subtract. If we do PQ, that means we're going to take the point Q minus the point P. Negative 3 minus 7 is negative 10. 0 minus negative 2 is 2. And finally, 6 minus 6 is 0. So that's a direction vector for this line. And to write the vector form, part A, the vector form is just L of t, and we'll take the vector whose tip is at 7, negative 2, 6, like that. That's P, secretly P there, or OP if you prefer the vector from the origin to P, plus t times u, which is negative 10, 2, and 0. And this is what we call the vector equation. The parametric equation is what you get by extracting the coordinate formulas for each of these. So for example, x of t is 7 minus 10t. The y coordinate is negative 2 plus 2t. And finally, the z coordinate is 6. It's just a constant. That makes sense because there's no motion in the z coordinate of the direction. The symmetric equations, we're not going to be focused on that. And finally, find parametric equations of the line segment determined by P and Q. So that's the dark part of this sketch. And what that means is, how do we limit the parameter in part B? So let me put part C in here. We're skipping that. Part D, how do we limit the parameter in part B so that it describes only P and only the chunk from P to Q? And if you look at it, you can see that 0 should be less than or equal to t, less than or equal to 1. In other words, t should go from 0 to 1. If t is equal to 0, then we have the point 7, negative 2, 6, which is the starting point. And if t is equal to 1, then we have p plus the vector pq, which is q. So note here that L of 0 is equal to P, or again, I keep conflating these two and I'll probably get worse as the semester goes on. L of 0 is the vector from the origin to P, and L of 1 is the vector from the origin to Q. So that's what they mean in the third part there. Find parametric equations of the line segment determined by P and Q. These are the parametric equations, and all you're really asked to do is figure out what t values correspond precisely to the part between P and Q and not the part outside. In problem 250, we are asked to, again, determine the equation of a line given some information. Find parametric equations of the line where we're given P we're given the point on the line and the vector direction. So here we're given the point on the line is 230 and the direction is the same direction as the vector that goes from Q to R. So let's work through that. All right, so the vector V, which is QR, can be computed by taking R minus Q. That's 0 minus 0, which is 0, 4 minus 4, which is 0, and 6 minus 5, which is 1. So it turns out this is just K. Not super important, but that just worked out. The vector form of the equation of the line is just going to be the vector from the origin to P plus T times the vector V. From the origin to P is just the vector version of 230, T times 0, 0, 1, like that. And from that you could extract both the symmetric equations, although I'm not asking you to do that, and the parametric equations. So this is the vector form, but you could get the parametric form easily just by pulling out the coordinates. For example, 2 plus t times 0, or 2, 3 plus t times 0, or 3, and then finally 0 plus t times 1, or just t. Find the intersection of the line with the xy plane. What do we know about points that lie on the xy plane? Yes, points on the xy plane have 0 z coordinate. So what is it going to take to get the z coordinate of this line to be equal to 0? Well, that means I need the third coordinate, z of t equals 0 plus t times 1. Fancy, messy way of writing just t. And I want that to equal 0 because I want the z coordinate to be 0. And what I learn is t is equal to 0. Now to find the point of intersection of the line with the xy plane, I go back and compute L of 0, and I learn that that's 2, 3, 0. We probably could have figured this out without doing too much work because we know that the point P lies on the line, and by virtue of its having 0 z coordinate, we know that it also lies in the xy plane. But this is a systematic way of answering that question. 254. In 254, we want to find the distance from this point to this line. So to find the distance from the point to the line, what we need is a point on the line and a direction. So let's just remind everybody of what this situation looks like. Here's the line. We've got a point A that's off of the line, and we know that the distance from the point to the line is this perpendicular segment that goes to the line. We need a point on the line in order to form this vector. And then we'll use the cross product identity to figure out the length of this piece. So a point on the line If you look at the parametric form here and you set t equal to 0, you get -1, t equal to 0, 0, and t equals 0, 2. This is a point on the line. It corresponds to t equals 0. It's not important that you choose t equal to 0, it's just important that you find a point on the line. Okay, we can find now the vector from P to A using the subtraction process that we're used to. So the vector from P to A is 4 minus -1, 2 minus 0, and 5 minus 2. All right, so that's the vector that goes from the point on the line P to the point off the line A. And we know that the distance, by our earlier work with the cross product identity, is simply the magnitude of the cross product PA with the direction vector. We need the direction vector. The direction vector is the coefficient on t here, -1, -1, 0. That's the direction of L, the direction of the line. So we need to compute the cross product and then divide by the length of the cross product. Of the direction vector. Okay, haven't done a cross product in a while. Let's do one real quick here. The cross product of PA with U is, we're going to use the determinant approach, IJK. We'll put PA in the first slot, 5, 2, 3. And we'll put U in the second slot, -1, -1, 0. And we'll start computing I times the quantity. 2 times 0 minus -1 times 3, that's going to be 3. Minus j, remember it's always minus j with the cross product. 5 times 0 minus 3 times -1, which is 3. And then finally plus k times the quantity. -5 minus -2. -5 minus -2 is -3. In component form, that's 3 minus 3 minus 3. And I'm just going to quick check my notes here, make sure I'm not making a dumb mistake. Looks good. All right, so what's the magnitude of that thing? We need the magnitude of that vector. The magnitude of PA cross U, square root of the sum of the squares here. 9 plus 9 plus 9 is 27, square root. And then to get D, we need to divide by the magnitude of U. What's the magnitude of U? U is over here, that's 1 squared plus 1 squared square root, that's square root of 2. So the distance from the point A off the line to the line is the square root of 27 halves. And the 2 is under the square root there. Okay? You can memorize this formula, but honestly, it's going to be more productive for you to just understand that this flows from the cross product identity and to derive it each time. I think it's more productive for you to be able to do that than to memorize the formula. 257. All right, we're going to show that the line passing through these 2 points is perpendicular to the line with the given equation. So the line passing through these 2 points is perpendicular to the line with the equation blah. So we're trying to show that it kind of looks like this. So that means we have to find the 2 direction vectors, say U1 and U2. Well, we know that the line through the points P and Q, U1, has the direction that's just the difference of these 2 coordinates. So let's just do PQ. So we'll take 1 minus 3, 4 minus 1, and finally -3 minus 0. So that's U1. What's U2? What's the direction of U2? Well, we're given the equations, the parametric equations. The direction is just the coefficients on the t in each of the three equations. So it's 3, 8, 6. 3, 8, 6. How do we know if they're perpendicular? We have the dot product for that. We can use the dot product to test for perpendicularness. Let's compute the dot product. U1 dotted with U2 is 3 times negative 2 plus 8 times 3 plus 6 times negative 3, and that's 0. So the lines are perpendicular. Do they intersect? Not necessarily. So the lines can be perpendicular, but they could also be skew and not intersect. All right, let's look at 262 here. So for the following two lines, or for the two lines, determine whether the lines are equal, parallel, not equal, skew, or intersecting. So what we want to do is first figure out whether they're parallel or not parallel. And we're going to do that by comparing the two direction vectors. So the direction vector for L1, we'll call it U1, is again the coefficients on the t. So it's 2. There is no t in the y equation, and there's no t in the z equation. So that's 2, 0, 0. That's the direction of L1. And the direction of L2, there is no t term in x. S is the parameter here. So take the coefficients on the parameter, and in this case the parameter is s, 1 and 1. So those are the two direction vectors. Are they parallel? No. Clearly these are not parallel vectors. If they were, one would be a scalar multiple of the other, and it's clearly not. Are they perpendicular? Actually, it doesn't really matter. We're not asked to figure out whether they're perpendicular. So they're either skew or they're intersecting. So they're not parallel, since U1 is not a scalar multiple of U2. All right, so they're either skew or they're intersecting. Let's see if we can figure out which. If they're intersecting, let's figure out when. Let's suppose they're intersecting. Then we should be able to figure out when the three coordinates are in agreement. So we'll look at x equals 2t, and we'll set it equal to x equals 0. And what we learn is that t is equal to 0 in L1 at the intersection. Okay, let's look at the y-coordinate. All three coordinates have to agree. So the y-coordinate of L1, 0, has to equal the y-coordinate of L2, 8 plus s. So in this case, oh, and I should note up here in the first case, s can be anything. So in the first case, the x-coordinates agree when t is equal to 0 and s is anything. In the second case, the y-coordinate, they agree when s equals -8 and t is anything. Now, when they both agree, when t equals 0 and s equals -8. So now we've determined that at this point of intersection, t is equal to 0 and s is equal to -8. We have to check z though. Do the z's agree? When t is equal to 0 and when s is equal to -8? Well, in L1, when t is equal to 0, what's z? Z is 3. In L2, let me make a little bit more space for myself. In L2, when, oh, and I should have noted up here also s equals -8, although it doesn't play a role. In L2, when t is equal to 0 and s is equal to -8, what can we say about z? Z is equal to 3. Oh, I think I'm looking at the wrong one. No, yes, in L2, when s is equal to -8, z is equal to -1. They don't agree. So our assumption up here that they were intersecting is wrong. They're not intersecting. And furthermore, they're not parallel, so they must be skew. Great. All right, problem 274. 274. Find the normal vector to the plane, express n using standard unit vectors, find intersections of the plane with the coordinate axes, and then sketch the plane. Oh, and you know what? Before I do this, let's go back. We had these two lines. Let's look at these lines in GeoGebra and see if indeed we're correct that they're not intersecting. So I'm going to go pull up GeoGebra here. GeoGebra has a really wonderful 3D plotting tool that's not too difficult to use once you get used to it. My link here goes to the 2D plotter, so I'm going to go to the main home page and go to the 3D plotter, which is down here, 3D calculator. There's probably a way to get there from the 2D plotter, I just don't know what it is. Cool. Let's plot a couple of lines. In the first line, L1, goes through the point 0, 0, 3. So I'm going to start typing the word line, and it gives me instructions on how to plot the line. I can give a point and I can give a direction vector, and that's what I'm going to do. I'm going to give the point, which is just 3 numbers, 0, 0, 3, like that. And I'm going to give a direction vector. That's I use the word vector here, and then give the direction vector, that's 2, 0, 0, like that. And we see the line, right? This is the line. It's going through the point 0, 0, 3, and it has the direction 2, 0, 0. In other words, it goes parallel to the x-axis, which is the red axis. Okay, so that's the first line. Let's do the other line. The second line, we'll use the same syntax, and we'll give it the point on the line. The point on this line is 0, 8, 7. And the vector, the direction of this line, is 0, 1, 1, like that. Looks like they're intersecting, but if we move it around, we quickly see that they're not intersecting. So from this perspective, it looks like they're intersecting, but in fact they're not. They're skew. They're not parallel. They're not intersecting. They're skew. All right, now 274. Problem 274 is about planes. Well, looks like I didn't get the copy quite down, so let's try that one more time. There we go. Have to be patient. All right, find the normal vector, find the intersection of the plane with the axes, and sketch the plane. Sketching planes is, well, sketchy, but we can do the other items pretty quickly. In part A, remember what I said? You can pick off the coordinates of the normal vector to the plane just by picking off the coefficients of the independent variables, 1, 0, 1. So n is the vector 1, 0, 1. Find the intersections of the plane with the axes of the coordinates. The intersections of the plane with the axes of the coordinates. So what does that mean? If I'm going to hit the coordinate axes, what's true? I'll go back to this GeoGebra sketch here. If I'm on a coordinate axis, what's true here on the x-axis is that both y and z are 0. So I can figure out where the plane hits the x-axis when y equals z equals 0. There's no y variable in here, but setting z equal to 0 tells me that x is equal to 0, and that's the intersection with between the plane and the x-axis. What about the y-axis? You guessed it, let's set x and z equal to 0. If we set x and z equal to 0, we get 0 equals 0. So what's the intersection with the y-axis? It turns out y can be anything. So it's the whole y-axis. Cool. What about z? Again, for the z-axis, we want x and y to be 0. We set x equal to 0, y is not present, we get z is equal to 0. And it can strike the z-axis, it strikes the z-axis at z equals 0. So if we look at this, we should find the plane hitting the x-axis at 0, hitting the z-axis at 0, and hitting the y-axis pretty much everywhere. Plotting planes in GeoGebra is also pretty easy. In fact, it's easier than plotting lines. Let me clear the display and show you quickly how to do that. You can just type the variables in. X plus z equals 0, and immediately gives you the plane. Here's the x-axis. Notice that it's hitting the x-axis at x equals 0. The blue axis is the z-axis. It's hitting the z-axis at x equals 0. And notice how it's hitting the y-axis. It's hitting the y-axis at every point. And that's consistent with our findings here. 280. All right, a little bit more sophisticated problem here. want to find the real number. We've got a free parameter in this equation for the plane. Want to find the real number that causes this plane to be parallel to this line. All right, so we've got a plane like this. We got a line that's kind of going like this, and the line has the direction u. And we know a little bit about planes too. We know planes have directions n. If this line is going to be parallel to this plane, what's the relationship between u and n? You guessed it. We need u to be perpendicular to n. Remember, we have a test for this. What we need is u dot n to equal 0. Okay, let's try that. Let's figure out the direction of the line. U is the direction of the line, and we can get that by taking the coefficients of the parameter 1, -1, 1. And n is the direction of the plane, and we can get that by taking the coefficients of x, y, and z, alpha, 5, and 1. We can compute the dot product up here is just alpha plus -5 plus 1. That simplifies to alpha minus 4. And what we've learned is that if we set alpha equal to -4, this plane will be parallel to this line. Let's confirm that over on GeoGebra. So we'll clear our earlier work. Let's plot the plane first, since that's easy. The plane is going to be -4x plus 5y plus z minus 10 equals 0. There's the plane. It's definitely a plane. All right, and let's go and plot the line. The line has this parametric form, and we're going to plot it in point vector form. So we're going to start with the line. When we type the word line, we get brief instructions or a reminder how to do this. We want a point and a direction vector. Points are just a trio of numbers. The point is 0, 2, 3. And the vector is the direction 1, -1, 1. Okay, there's the line, there's the plane. Not super sure whether these are parallel. We need to kind of twist it around and see. Oh, and I must have made a mistake. Let me check my notes here really quickly. I see it. Alpha minus 4 equals 0. Alpha equals 4. So if we go back over to GeoGebra, let's go here and fix our plane equation. Let's get rid of that minus sign. There we go. Now, are they parallel? Let's move it around a little bit, and indeed they are parallel. It might at times not look like they're parallel, but that's just because GeoGebra has this kind of 3D perspective thing going on, but they are indeed parallel. All right. Problem 290. Problem 290, we want to find the distance from the point to the plane as specified. Similarly with the other example, here I think it's best to just work from first principles. So we have a plane like this. It has a normal vector like this, which we can identify from the equation. And we have a point, P, sitting out here in space, presumably off of the plane. We take any point on the plane, call it Q. Any point on the plane, call it Q. And connect Q and P by the displacement vector, P, let's call it QP, like that. And what we want to do is project that vector onto the n direction. We want the scalar projection of QP onto n, and that distance will correspond to this perpendicular distance here. Remember from our earlier discussion, d is going to be the component in the n direction of the vector QP. And we write that as the absolute value of QP dotted with n over the magnitude of n. So the first thing we need to do is find a Q on the plane. And what that means is you stare at the equation of the plane and you try to find a point on the plane. What I usually do is just, if possible, like since I'm trying to set this thing equal to 0, I just try to make each of these three terms 0. So I know if I plug in x equals 3, y equals -1, and z equals 0, it'll satisfy the equation. So Q, 3, -1 and 0, that's going to lie on the plane. So then the vector QP, again, I can just take P minus Q, so 1 minus 3 is -2. -2 minus -1 is -1, and 3 minus 0 is 3. So there's the vector from Q to P, and it remains to just compute the scalar projection onto n. Let's figure out what n is. Remember, we can just pick off the coefficient on the x, y, and z variables. In the first slot, we get 1. In the second slot, the 2 is going to distribute onto the y, so it's 2. And in the third slot, -4. So there's a normal vector for the plane. Let's compute the dot product and similarly the distance. The dot product is -2 plus -2 plus -12. And we're going to divide by the length of n, 1 squared plus 2 squared plus, 1 squared plus 2 squared plus 4 squared. That's 1 plus 4 plus 16. That's 21 and square root. In the numerator, we have 12, 13, 14, 15, 16 absolute value, and we get 16 root 21. Let me check my notes here, make sure I didn't make an arithmetic error. That looks good. Okay, so again, from first principles, I know that I just want to project this vector from any point on the plane out to P onto the normal direction, and that's going to give me the length of this line segment. 298. So in 298, we have a plane with this equation, and we want to find the equation of the sphere with center at the origin that is tangent to the plane. So I'm going to draw the plane again. Again, we're just drawing generic planes. And let's put the origin out here. Remember, the origin is just 0, 0, 0. And we've got a normal vector. Planes have normal vectors. We can figure that out later. What we need to do is we need to figure out the distance from the origin down to the plane, because we'll use that distance as the radius of a sphere. and that sphere will then be tangent to the plane. So our first job is to figure out the distance from the origin to the plane. This is very similar to the previous exercise. We need to find a point on the plane, Q, and then compute the vector from Q out to O, the origin, and then project that onto the normal direction. Let's do that real quick here. So we want to find a Q that lies on this plane. Why not take 8, 0, 0? 8 minus 0 minus 0 minus 8 is going to be 0. So let's let Q be 8, 0, 0. And let's find the vector from Q to 0, to the origin. The vector from Q to the origin is just the origin minus Q. So it's that vector. And then to project it onto the n direction, let's figure out what n is. N is going to be 1, negative 1, negative 1, like that. And then the distance we know is going to be the scalar projection onto the n direction. And we know the scalar projection is just QO dotted with n over the magnitude of n. QO dotted with n is just 8. And the magnitude of n is just the square root of 3. So the distance is 8 root 3. Now don't forget what we're doing here. Find the equation of the sphere with center at the origin that is tangent to the given plane. So we want the sphere whose center is the origin and whose radius is 8 over root 3. So the equation of the sphere is x squared plus y squared plus z squared equals the radius squared, 64/3. Now if we've done this correctly, we should be able to plot both this plane and this sphere, and we should see that tangency happening over in GeoGebra. Let's do that. We'll clear our earlier work. Let's do the sphere. The sphere is pretty easy to type in. X squared plus y squared plus z squared equals 64/3. It's a nice looking sphere. And let's get the plane. The plane is x minus y minus z equals 8. X minus y minus z equals 8. Okay, not sure if they're tangent yet. Let's move it around and try to get a look at that point of intersection. My computer's struggling at the moment, but if you sort of take it really slow, you can see that indeed the plane and the sphere are tangent to each other. And this distance from here to here is 8 over root 3. I'm going to stop there and let you find the parametric equations of the line passing through the origin and the point of tangency. So you're trying to find the equation of this line down through here. Okay, suggested exercises. I want you to do all, or at least consider all of the exercises in section 2.5 except for these three, 299, 300, and 301. What's special about those three? All of these are talking about, let's see, 299. Gosh, I don't remember why I excluded these. Oh, I think I don't want us thinking about these parametric curves just yet. We're going to get there soon enough, but let's talk about them when we get there and not at this point. So I think that's what I didn't like about them, was these parametric curves. All right, so again, just do enough of the exercises to get acquainted or get the the ideas settled in your mind, and then jump over to WebWork and do the assessment for Chapter 2, Section 5, Lines and Planes. Thanks.